physics colloquium, I just want to say that colloquium is a word whenever it is used in the context of physics. That means that advanced topic would be discussed or presented to a set of people where the people may not have very little knowledge or may have zero knowledge about the subject, but it would be presented in a very interesting way. So why we thought about this LNMIIT Physics Colloquium series? Because we think that this kind of colloquiums will basically ignite the interest in young minds. So we will give you an opportunity where very prominent researchers, you would be able to listen to them and their research work. But the way they will present is not very in a technical manner, so you will be able to understand most of it. So this is just the first colloquium of this series. We think
And the pointer also.
yes.
Okay. So I'll speak slowly. And first thing I would like to tell the students that you can stop me anytime and ask questions. And even if you find that the question, for some reason, you could not ask a question or you are listening it from YouTube. So just note my email address and my phone number is almost a public number that's available in internet also. So if you have any query, you can drop me a message also later on. So this was as Professor Vishwas introduced that the idea of Colloquium, this will be a popular talk, but with on a highly technical topic. And when I planned, I thought that I'll give you a brief history of the thing. What is the state of art? Where is the open problem? And where our young students can make career. So to begin with the review kind of things, so I'm showing some popular pictures. So in extreme left, you can see these pictures of IBM and almost a similar picture of Google in the next picture in the top row, second left. So what is this? So often people think that this is the quantum computer, but this is not quantum computer. The what you see, the golden color thing outside is actually called a dilution refrigerator. So this dilution refrigerator is used for cooling, and the quantum computer is somewhat like a chip as shown here in the second row left hand side. So these are superconducting quantum computer. So superconducting quantum computer requires that it should work in a very low temperature. So one of my former student, another undergraduate intern, now work in Stanford, and he works on a quantum computer which works at 4 Kelvin, and they call it high temperature quantum computer. So even 4 Kelvin is high temperature because this works even more low temperature in millikelvin range. Now, in science, there are many things. There are international politics, many other aspects. So this dilution refrigerator is a kind of monopoly. So only one company from Finland makes it. Now they have created an embargo that they will not sell this dilution refrigerator to China. But China is building many quantum computers, so they need to build this dilution refrigerator. In India, nobody makes this dilution refrigerator so far. So the technological challenges to become technologically independent in quantum computing is not restricted of building a quantum computer. We have to develop this kind of peripheral technology also. And there are, so it's not like that this technology is not available, but we are dependent on another country for making this device called dilution refrigerator. So in short, this big thing is not quantum computer. There is a small chip inside, and that's quantum computer. But this is a particular kind of quantum computer, superconductivity based quantum computer. Now you come to the third one, a molecule, CH3Br is shown. So is it a quantum computer? The answer is yes. It looks like chloroform. So this was used in NMR based quantum computing as a quantum computer. So we actually use the nucleus and we count the number of independent Lamarck frequency. So if there is a nucleus which has 3 independent Lamarck frequency, it can work at most as a 3-qubit quantum computer. So I'll show that in India, the initial works on quantum computing started with NMR based quantam computing at IISc and at Professor Anil Kumar's group. And then we used to have, so all of us means who are working on quantum computing, quantum communication for long, all of us started this thing about 27, 28 years ago, somewhere in that time. And then they did an experiment with this kind of molecule and this kind of nucleus. And this quantum computer is actually in a test tube, and then it's a formal NMR. So we used to have a joke that somebody came to Professor Anil Kumar's lab and asked that, where is your quantum computer? And he told that I have washed it out because it's in a test tube. Now, there is a version in the middle between the nucleus and the NMR thing, the top second right. And this is a photonic quantum computer. So photonic quantum computer, the advantage is that it can work in room temperature. But the difficulty is that photon flies. You cannot keep photon in one place. You can keep a nucleus spin in one place, but keeping a photon in one place is very difficult. So now you all know that there is a national quantum mission in India, and in national quantum mission, there are several TGs, and the TGs are supposed to technical group, thematic groups. They're supposed to build different technologies. So I am part of one group in which we are supposed to make a photonic quantum computer. But there is another group, they will make a photonic quantum computer. Their photonic quantum computer will be integrated optics based. Our computer will be bulk optics based. So we are interested in, so what is the difference between this different kind of quantum computer? So the realization of qubit is a quantum bit is different in this different kind of quantum computer. So a qubit in essence is a 2-level quantum system. So any 2-level quantum system you can treat as a qubit, and different kind of 2-level quantum systems are used in different systems, and that leads to different technology for quantum computing. Now, if you write second column from top, write second picture from the top, this is an ion trap quantum computer. And ion traps are also a very good candidate because most of the times in ion trap realization, all the qubits are connected to each other. So what does it mean? I will tell you later. But all these these are quantum computing infrastructures at different places, the different kind of realizations of quantum computing, and they can often show some, or they're expected to show something called quantum supremacy. So what is quantum supremacy? Quantum supremacy means to demonstrate that it can do a task much faster than what all its classical counterpart can do. So classically, some task needs a few thousand years, and a quantum computer can do it in milliseconds, then it's quantum supremacy. But suppose classically it can be done in 2 seconds, quantum computer can do it in 1 second. That's just a quantum advantage, that's not quantum supremacy. So in the left, we are showing our balls are falling and then the samples are collected in some shape. So this is the problem. This is called Boson sampling problem. And in context of Boson sampling and Gaussian Boson sampling, quantum supremacy has been claimed. So I stress on the word that has been claimed. That means it has not been established without any criticism. So there are some criticism, but we are very close to establish criticism-free quantum supremacy. In the bottom center, we are showing a picture in which there is a satellite, but satellite is not connected. And you can see that there is a ground station which is connecting with the another ground station. So this is the most popular picture of quantum communication or quantum cryptography, which is satellite assisted. So we'll come back to this. The greatest success is that China and Australia did a conference with a key which is generated using the quantum resources. So it was a quantum secure conference, and that was assisted by satellite. We are interested in that, and probably within 3 years, our own organization, ISRO, will be able to show satellite assisted quantum communication. So all these things, you see, this quantum computing, quantum communication, these are new applications of quantum mechanics, and they are called second quantum revolution, as I'm showing in the right bottom. So what is this second quantum revolution? So when I say something second, then there is something definitely fast. So what is the fast? So today you are using laser. So first you understand the meaning of the word quantum. The word quantum means discrete. Classically, all values of a physical observable is allowed. So for example, you can run with a velocity 30 km per hour, 20 km per hour, 20.9 km per hour, 20.91 km per hour, but quantum mechanically it becomes discrete. This discreteness in energy is required for formation of semiconductor. So if all energies were allowed, then there was no conduction band, no valence band, no band gap, no laptop, no iPad, no mobile phone. There is no semiconductor. Today we do so many things with the laser, but laser is possible only if there are at least three discrete energy level, and one of them is metastable. So all these things, transistors, lasers, are product of first quantum revolution, and now we are interested in second quantum revolution. So as the title suggests, we want to move. We are in an excursion. So you've joined me in the excursion in the world of quantum computing and quantum communication. So in the quantum communication, everything happens between Alice and Bob. And Alice is always a girl, Bob is a boy, and there is an eavesdropper. And eavesdropper Eve is a bad girl who want to read the information which is not intended for her. So now Bob is asking Alice, you went to Wonderland. So you all know Alice went to Wonderland, Alice and Wonderland, but do you know where is the land of unconditional security? So what do we mean by unconditional security? I'll come back to that. And Alice answered that, yes, Bob, I know that. So Alice asked that, can you go there? So as if you were asking me that, can you join me in that excursion? Can we go together to the quantum land? So see the interesting answer that you have to take a space-time craft. So it's not only space. So moving from Jaipur to Delhi will not take you to a quantum land. You have to go ahead in time. So what does it mean? Certain technologies are not yet available. So you need further development of technology, and as we progress with the talk, you will gradually know about what are the technological problems, which are the challenging problems which are open, which you can address. So certain problems cannot be addressed because they are fundamentally not allowed by physics, but there are many problems where we know that physics allows it, but no technology is available. So I'm speaking from Noida, which is just suburb of Delhi, and these are some part of our institute. And in one of this building, I have a small lab, and we do quantum cryptography in this lab. And as I mentioned, that it all happens between Alice and Bob. So my Alice and Bob are sitting in the same box. They are on the same table. But you can see some wooden box in the middle, in the rightmost top picture. So this wooden boxes contain 40 kilometers of fiber. So they all together, I have 120 kilometer of telecom grade fiber, and I can separate my Alice and Bob by 120 kilometer and do quantum key distribution. So let's join the excursion and we move to quantum light. So some recent news and some resources that you may use. So you see that IBM will release the largest ever quantum computer in 2025. It is expected. So here I am. You know that IBM gives free access to their quantum computer. You can type quantum IBM quantum experience and go to quantum.ibm.com, and even from your Android phone, you can access quantum computer over the cloud. So now in the right hand side, I am showing some quantum computer from, so this is a screen from Kuafu. Kuafu is a quantum computer provided by Beijing Academy of Quantum Information Science Pakis. The link is here. And you see that this 108, the top one is the 108 qubit quantum computer. 156 is 156 qubit quantum computer, and all these are free for access. And QTIP is a tool, it's a Python-based tool for primarily doing quantum optics, but this is very useful for doing many theoretical works, and you can access small quantum computer from your laptop, and you can run you can do many things using QTIP, etc. So these are some lists which you can use, and IBM quantum computer and Kuafu are free, but Amazon bracket gives you access to several other quantum computer which is not free. But for teacher, there is another window. So those who are attending and who are faculty, you can write a small project to MIIT, roughly 2 pages project, and request for access, and you can use Amazon bracket, and MIIT will pay for your access, and this kind of projects are called cohort. Anyway, so I guess many of you have SBI account. So let me do one experiment with you, and then you will understand that why we need quantum technologies. So I'm just stop sharing the slide. I'll come back to the slides, and so I share my screen, and if I write sbicard.com, so you can also write, you can see SBI. Can you see the SBI in my screen?
Yes, yes.
Now you see that there is a lock. So this lock means, and if I click on this lock, it is showing that connection is secure. So now I click on this, and then I click on more information. So in the more information, you can see that this connection is encrypted, and it's coming like TLS ECDHE. So what does it mean? TLS is a handshake protocol. ECDHE stands for elliptic curve Diffie-Hellman encryption. RSA is name of 3 people, and then with AES 128 bit, and SHA-256 is a hash function. Hash is a one-way function. Whenever you type your password, the password is not gone in the channel directly. Password is encrypted with a one-way function. So we have many ways to hack your password. So one such way is to do something called dictionary attack. So normally you give password which you can remember, and then you may change A into @ S into $, and because you have to remember the password. So these are normally dictionary word or part of your name, part of your hometown's name, etc. And we can create all such password and create their hash function and compare the hash function and find out your password. Now, if you give a very difficult password, you cannot remember, and then you put it in your wallet. If wallet is stolen, your password is stolen. So your password ideally should have 2 pieces, one part which you can remember and one part which you cannot remember is in the wallet. Anyway, so elliptic curve Diffie-Hellman, these uses some mathematical problems. Diffie-Hellman use something called discrete logarithm problem. EC use elliptic curve. RSA use odd biprime factorization problem. So these problems are very difficult to solve, and that leads to security. And before we progress, I just want to tell you that this EC Diffie-Hellman and RSA both are vulnerable if a quantum computer can be built. So all these problems cannot be solved in the classical world within a stipulated time, but quantum computer can solve them quick enough. So what I have shown you that I'll elaborate on this, that your SBI is not secure if a scalable quantum computer can be built. We return back to our slides. So I was just make such a slide that you click here and you see that. So few years ago, means we did some study how vulnerable are Indian banks from a cryptographer's view, and shared most of the report which cannot be shared publicly with some officials with RBI. But anyway, so this is the this line is important for us. And now, so to understand that why SBI is vulnerable, I have to understand certain things. So in the school, we were, or even for the faculty, even if you receive something from dean that in your question paper, some problems must be very difficult, some problem is to be easy, some problem is moderately difficult, but how do you count the difficulty level? So here we show you the first thing I want to tell you that about algorithm. So we calculate something called complexity of the algorithm. So complexity is counted in terms of how many steps it need to solve the problem. So first thing let us define is, let for ease of discussion, let me define that what is algorithm. So algorithm is a systematic procedure to solve a computational problem. So what is the first algorithm you learned? Most of us learned a systematic procedure to add a two-digit number to a two-digit number. So you used to write, say, 12 and 34. So unit place below unit place, 10 place below unit place, 2 plus 4 is 6, 1 plus 3 is 4. So 46 is 12 plus 34. And who taught us this? So first teacher who taught us our first algorithm is probably our mother. So algorithm has nothing to do with computer. Now you see that if there is a two-digit number, to add two-digit number, you need two steps. Three-digit number plus three-digit number, three steps. Four-digit number plus four-digit number is a four step. So a n-digit number addition involve n steps. So this n is its complexity. Now you compare the multiplication, 12 into 34. 2 into 4 is 8, 1 into 4 is 4, 2 into 3 is 6, and so on. So you are doing 4 multiplication and 3 addition. So addition of two-digit number to two-digit number involve only 2 steps, but add multiplication involves 7 steps. So what we learned, multiplication is more difficult than addition. Factorization is even more difficult. We have to check many factors. So if I take two large prime numbers and multiply and give you the number, and you have to find out the factorization, you have to divide by 3, 5, 7, all the prime numbers till root n to find out the factor. So if the factors are bigger, the problem is more difficult. So when it's a biprime, means there are only two prime numbers, only two factors, then it is difficult. And if it is odd, it is even more difficult, because in case of even, you know that it is one factor is 2, and it has to be square free, because we have good algorithm for find out square root. So a difficult problem for classical computation is one in which you have to find out the factors of odd by square phi by prime, and that leads to the cryptographic scheme called RSA. So this is the background problem. So if one has to break a RSA code, one has to factorize. So classically, we don't have any algorithm which can perform the factorization in polynomial number of steps. For polynomial of what? Polynomial of n. So in case of addition, we tell that if the size of the problem is n, there are n digit, I need n steps. So if there is a task which we can do in n steps, n square steps, n cube steps, or shorter than that, so then we can, or in any polynomial, we say that it is solvable efficiently or within reasonable time. So such problems, in the look at the left hand side picture, such problems belong to a class called P. So P, all the problems which can be solved in polynomial number of steps in classical computer is called P. Now there are problems which we cannot solve deterministically in P number of steps, but if we allow some error, we can solve them probabilistically and with a bounded error. So class of such problem is called BPP. And if you can solve such problems with quantum resources, that's called BQP. So I have shown a region which is BQP, and you can see that it is much bigger than P. Now there is another interesting class called NP. So NP are those problems. If I give you the solution, you can check it in polynomial number of steps that it is solvable or not, but you cannot, there is no known algorithm. So NP includes everything. So P is a subset. So now you see that P is a subset of NP and there are problems outside P. So these are the problems for which we don't know any algorithm which can solve it in polynomial time. But I cannot prove that somebody tomorrow will not be able to design an algorithm which can solve it in polynomial time. Now, if this part is clear, this is very fundamental for understanding the computing. Now, you can see that PQP span over P. So there are problems which classical computer cannot solve deterministically in polynomial time, but using quantum resources with bounded error, you can solve it. But this picture shows that there are some yellow region outside BQP in NP. So there are problems outside BQP in NP. Now, how classical cryptography works? In classical cryptography, always there is a background problem, and we pick a problem from NP, which is outside P, and construct a cryptographic scheme. So to break it, one has to solve a mathematical problem very quickly or in polynomial time, and there is no algorithm. Now, this is conditional because you are assuming that if you don't know algorithm, your enemy or eavesdropper also don't know an algorithm. You are assuming on computational power of the other. So for example, when I'm using 128-bit secure key, I'm assuming that a 128-bit odd biprime cannot be factorized by my enemy within the time frame for which I want to make the system secure. Now there are many things in computer science which is like religion, which is believed, but there is no proof. So we believe that quantum computer can solve only problems in BQP class, and there are problems outside BQP, which is called in NP. So if we construct a problem, cryptographic scheme from that, then that will be secure even when a scalable quantum computer is built, and that is called quantum safe, and this is called PQC, post quantum cryptography. So post quantum means a quantum computer is built, still a classical cryptography is secure. But we really have no proof that P is not equal to NP, or quantum computer can solve only BQP problem. PQP is subclass of NP. But if we believe these things as in computer science, then PQC has the greatest business at the moment. So if some of you are thinking of working on cybersecurity, so the products which you can sell most is some solutions which involve PQC, because quantum cryptography will require infrastructure, a new infrastructure, new type of optical fiber, dark fiber. PQC does not need any such thing. And if you have a next generation of operating system, it will have PQC. 6G will come with PQC. Okay, now to have a great, so this was a bit difficult, not very difficult. I tried to make it lucid, but to make it further lucid, what do we mean? Now you see that there was an exam and the student has got F grade, and the teacher told that you have got F grade, you are not studying properly, and the student told that, well, all the problems were in NP, so they cannot be solved in 3 hours of exam. And teacher is saying that if you don't study well, it will appear in NP. This may happen with our perception about the algorithms also. So it may be that we have not studied well, that's why it is appearing in NP, but tomorrow somebody may come out with a solution which is P. Now, when we calculate algorithmic complexity, we calculate always in the worst case scenario. To elaborate that, we have a cartoon here. So there is something called Grover's algorithm. Grover is an Indian and he has a famous quantum algorithm. So Lob Grover was born and brought up at IIT Roorkee. His father was a faculty in IIT Roorkee. Then he graduated from IIT Delhi Computer Science and went to US. And he designed an algorithm for unsorted database search. So what is unsorted database search? So as an example, teacher told that, well, we have a telephone directory in which it is ordered according to the name. And I give you the phone number and you have to find out the name. So if you are doing a crude search, sometime you will do it in the first random search. Sometime it will take n. On an average, you need n by 2. Classically, you need of the order of n searches. Quantum mechanically, you can do it using quantum resources with root n searches. So if n is 4, n by 2 is also 2, root n is also 2. There is no difference. But when n is 10 to the power 16, n by 2 is of the order of 10 to the power 16, but root n is only 10 to the power 8. So you can see that when n increases, how the differences increases. Now, this question is asked in a class that I give you a phone number and you have to find out the name of the person from a telephone directory. How many searches you need? A student told that I need only one search. I'll take my mobile phone, call him and ask his name. But This may or may not work. The man may answer, may not answer. He may tell his name. He may disagree to tell his name. So we don't calculate anything on best possible scenario. We calculate the complexity in the worst case scenario. So as I was telling that nobody knows that P is equal to NP or not. And till few years back, the situation was very bad. And we had only a handful of quantum computer. They were like Grover type. They were Fourier transform based, like Shor's algorithm. I'll come back to that. And algorithms for simulating or solving problems. So that time, Peter Shor, one of the greatest contributor in quantum computing, Peter Shor wrote an article, why have not more quantum algorithms been found? And he gave two logic. One is that we live in a classical world, so we think classically, and we don't have a quantum computer with which we can, by trial and error, by playing, we can design new algorithm. Now, since IBM introduced the free quantum computer, you can access cloud-based quantum computer. Then Quafu is given cloud-based quantum computer. You can access to Amazon. So now, so many students, so many people have, and we have so many brains working on it. So naturally, the number of quantum algorithms are increasing, and new is expected that very good things will come. And of course, all the audience, students can feel encouraged, and you can contribute in this effort. So some points I want to note. Algorithms can exist and evolve in general without any kind of computer, as I have mentioned about the addition. Quantum computers can show supremacy if quantum hybrid, quantum inspired algorithms can be built. So all algorithms are not essentially quantum. Often they are hybrid. Computing is possible only because error correction is possible, but we need to design algorithms with a laser amount of error correction overload. So at the moment, for 1 qubit error corrected qubit, I need at least 5 qubit. So IBM Surflies have a 5 qubit free quantum computer. So that will essentially become error corrected 1 qubit. So old algorithms like Euclid's GCD, which dates back, this is before Christ, is still used in Shor's algorithm. So now algorithms can be quantum, hybrid, quantum assisted, uses quantum resources, and of course classical don't need. So development is there, and what I say now, we are in an era called NISQ. So this is noisy intermediate scale quantum. So quantum computers are not very small, but they're not very big, and they're noisy and they're intermediate scale. So we are going for the ideal situation is that we'll go for a fault tolerant quantum computer. But at the moment, what kind of things we are doing? So we are designing quantum algorithm. So it's all about the speed up. So if a classically it can be done in n square step and quantum mechanically you need n cube, nobody is interested. So classically, if it is done in n square and you can do it in n or log n or n log n, then only it is interesting. So you have to beat, as far as complexity is concerned, you have to beat the classical thing. So we design algorithms, and there are class of algorithms. So there is certain class of algorithm called promise algorithm. So Deuys and Deuys-Josa algorithms were the early algorithm, which were a promise algorithm. So what kind of promise algorithm? The task is like this. So suppose there is a function f of x, and x can take 100 values, 0 to 99. So either for all such values, f is constant. So f of 0 is equal to f of 1 is equal to f of 2 is equal to f of 99, and it is equal to 0 or 1. Or half of them are 0 and half of them are 1. Then we call balanced. So 50 of them are 0, 50 of them are 1. We are not interested that which one is 0 and which one is 1. So think there was a simplest case, Deuys algorithm. So there is a coin. So either both side is head, both side is tail, that is constant, or one side is head, one side is tail, that is balanced. But to know that whether it is constant or balanced, for a coin, you need to see both sides of the coin. Classically, you need two searches or two observations. Quantum mechanically, you can do with one observations. So even if it is 100, and you have to check that whether 50 of them are 0 and 50 of them are 1, that is balanced, or all of them are 0 or 1, that is constant. Classically, you need 50 plus 1, 51 searches when there are 100 samples. Because even if I told you that we calculate in the worst case scenario. So in the worst case scenario, you can get that you have a balance, you have a constant thing, but all the first 50 observations lead to 0, and then only the 51st observation. But if you see that 51st observation is also 0, then you are for sure that it is a constant function. But if all 50 are 0, it's highly likely constant, but you cannot say that it is constant. Grover's algorithm I mentioned. Shor's algorithm is for factorization of odd biprime. So you see that classically we need exponential of the order of log n to the power 1/3. So anything exponent grows very fast with the n. Quantum mechanically we need only log n cube. So log n is even smaller than n. So this is smaller than n cube. So this is polynomial. So what we are saying that classically you cannot have a algorithm for odd biprime factorization which can solve it in polynomial time, but quantum mechanically you can do it. But still, so what is the problem? The problem is discrete logarithm, which leads to Diffie-Hellman. The problem which Shor's algorithm can solve is called odd biprime factorization, which is the background of RSA. And so if you have a scalable quantum computer to implement Shor's algorithm, then classical cryptography is vulnerable. So quantum cryptography appeared in 1984, but it became popular only when we can show that classical cryptography is vulnerable. But still, why we are using classical cryptography? Because quantum qubits are prone to noise. There is some problems called decoherence. So we'll come to that. Then today, everything we are doing is primarily VQA, variational quantum algorithm, but it's all mean to speed up. And variational quantum algorithm is a family which has two parts. One is called VQE, one is called QAOA. So VQE is variational quantum eigensolvers and QAOA is quantum approximation optimization algorithm. So in implementation of all this, there is a classical part and there is a quantum part. So these are essentially hybrid algorithm. So I do certain things in quantum algorithm and I do certain things in classical computer. So I can do some kind of parameter optimization in the classical computer, but the problem is that by the time I finish this optimization in classical computer, quantum computer gets switched off because the qubits decohere very fast. But using even these facilities, people have done many interesting works and claim to show in boson sampling and Gaussian boson sampling some kind of quantum supremacy. We have factorized very large number. Well, personally, we have factorized only 35, but with a very small register. And the intention is to show supremacy by a well-defined problem, quantum supremacy, where a quantum computer will do a task much, much, much faster than classical counterparts. Now, how classical cryptography work? I already mentioned that two primary things is RSA and Diffie-Hellman. There are other things. In the background, there is a computational problem, and we assume that how we decide the size. So if you have a 2G, I show you that SBI using 128-bit encryption. So 128-bit encryption that you need to half an hour, it will remain secure. If you use 2048-bit encryption, it will remain secure till 2040. So you are just increasing the size of the problem. So when you increasing the size of the problem, it's become difficult for your enemy to factorize or solve the discrete logarithm problem. But the problem is that this is condition. This is conditions on the power of somebody else's. So to understand or give you a clear visualization of what is conditional security, you put a lock at your hostel room and go out. Is your lock unbreakable? Somebody just need a hammer or a hacksaw blade to cut the lock. Yeah. But you have a trust that such kind of things will not happen. So it's a conditionally secure. It's secure provided somebody is not coming with a hammer. Cryptographic situations are very interesting. So I give you a cryptographic situation where Alice and Bob are as usual involved. Here, Alice and Bob were husband and wife. They had a good life, but then they fought. And you know that when marital fight happens, they don't believe friends. So they don't believe somebody is marked as Alice's friend. Some people are marked as Bob's friends. They don't want to see each other. But they don't want to toss a coin and decide that who will keep the house or who will keep the pet dog or something like that. Now they want to toss, but remotely. Now, if Alice tosses the coin and tell that the outcome is head, Bob will tell, oh, that's my bet. And if Bob tells that my bet is tail, Alice will tell that, oh, head has come. So what is the solution? So the classical solution is like this. Alice will toss the coin, put it in a box, lock the box, keep the key with herself, and send the box to Bob. Bob will, after receiving the box, Bob will send the bait to Alice. Now, after receiving the bait, since when Bob is sending the bait, the result is already with Bob, only thing that Bob cannot see. So Alice cannot change. And after receiving the bait, Alice cannot do anything because the outcome is already with Bob. Alice sends the key, Bob opens it. Now, this apparently fine solution as a problem. We are assuming that the moment the lead box is received by Bob, Bob cannot break it and see what is inside. Okay, so we are putting some conditions on the muscle power of Alice if it is a Bob, if it is a physical law, and computational power of Bob if it is a digital law. So this is the sense of solving a computational problem which leads to cryptography or security in classical world, and that's why it's called conditional security. In contrast, I'll show you that in quantum cryptography, we don't need any such thing. We use laws of physics. So I'll come to that. Here we are showing one of our paper in which we use IBM quantum computer to factorize 35. And I used to joke with my students that if your younger cousin asks you that what you are doing for PhD, and you will tell that I prove in my PhD that 35 is equal to 5 into 7. Such small things are also important, provided that you have a new unique scheme of doing factorization, and it lets less quantum overhead. So we do different kind of things with quantum algorithm. I'm just showing something. So for people who are interested in condensed matter, so Majumdar-Ghosh spin chain model is a generalized version of things like Ising model, and there's a max cut problem, which is a computer science problem. We use variational quantum algorithm to solve it. And why the so much interest in VQA or QAOA? So this can solve optimization problem. And in art, most problems are optimization problem. Be it dark designing, it is an optimization problem. You will invest in a stock market, it is an optimization problem. The flight scheduling, it's an optimization problem. So most problems on earth is optimization problem. Quantum, these QAUA are showing much promise for solving optimization algorithm, and there are a lot of job at the moment on optimization problems. So students, if you want to build a career, the physics is no more restricted that you have to do a master's and then PhD and then postdoc and then become a faculty or a teacher. It's not like that. You can go to industries, including software industry, pharmaceutical industry, drug designing, many such places. Name anything, there is some application. At the moment, it is in peak. Everybody has a technology watch group there because the scalable quantum computer is not ready, but each industry wants to remain ready with their software, their algorithm, so that when the hardware is available, they immediately can take advantage of that. If for some reason hardware is not built, these jobs may reduce. But where we stand today, physics is in highest promise, means that of course, these things are not restricted to physicists. Many mathematicians are doing very good. Many computer scientists are also very good. But learning quantum mechanics can be rewarding at this moment. Now, the question is, so let me make it a bit lucid, how it all started. So I promise that I'll tell history of the subjects in between. So quantum cryptography started in some sense in 1970. So the people involved was Stephen Weisner and Charles Bennett. The most famous protocol of quantum cryptography is called BB84 protocol, and this is Bennett and Brassard. So this is a handwritten note by Charles Bennett, and you can see the date is 24th February 1970. Stephen Weisner was his classmate in undergraduate, but then in postgraduate they were in two different places. They were Jew, and Stephen Weisner was Jew, and there was no synagogue in the place where he used to work, and so he used to visit Bennett. And in during one such weekend visits, he told about an idea that to use quantum mechanics to stop forgery of currency notes. So he called it, say, quantum cash or quantum currency note. So what was the idea? The idea was that instead of 1, 2, 3, 4, some numbers in the note, in currency note, there will be some qubit. So qubit is a two-level system. The problem is that quantum states cannot be cloned. Why it cannot be cloned? You all know Heisenberg uncertainty principle. So I give you a lucid idea. If you can clone a state, in one copy you will measure position, in another copy you will measure momentum, and Heisenberg uncertainty principle will be violated. It's not a tight statement, but something like that. So no cloning will stop give you the idea of no forgery. But he sent this article to a wrong journal and system was not ready and it was not published. Much later, there was a conference in Puerto Rico and Brassard was swimming in the sea and Bennett went there swimming and in middle of the ocean, quite far from the beach, uh, he told him about Stephen Weisner idea. It was a very unusual place to discuss. And by the time they came to beach, they had the idea of BB84 protocol. But this happened in 1980 and they found it very difficult to publish. So they presented in Brazil, but they published only in abstract. So then there was a conference in India. So this is the India link in the beginning. So Bijay Bhargava was a faculty in IISc and he was organizing an IEEE conference and Brassard was invited. And in Brassard's onward, considering how difficult it was to get these ideas publishing at that time, the resulting paper said, so he decided that he will present and that this resulting paper published in BB84 protocol in a conference proceedings of a conference organized at IISc Bangalore. So in early Indian works, I mentioned about Grover. So this is Grover and this is Umesh. So Umesh Bhajirani and Grover gave very good idea of quantum complexity theory. Arun Pati started publishing very early. So this is Arun. So some theoretical work from India, some from abroad, but I mentioned you that there was experimental activity and Deutsch-Josha algorithm was written. This is a theoretical work for continuous variable, Samuel Bernstein and Arun. But experimentally, for discrete variable, Deutsch-Josha algorithm was realized by Kavita Dorai. She is now a faculty at ISR Mohali. Arvind is also a faculty in ISR Mohali. And Anil Kumar, who was Kavita's supervisor in IISc. And this is the molecule which I show was used for realization of Deutsch-Josha algorithm. So many people now say that first Indian quantum computer is built in TIFR in this year or last year. But if these are all special purpose computer and this was realized in 1999. So we were more or less at par with the world at that time, but gradually the experiment did not develop so much, but there's a very good amount of theory done in India. And with now we have a great hope with National Quantum Mission that will again do best things. So different aspects of secure quantum communication and computing, view of current incident. So you see, in third world countries, corruption is a big thing. The corruption and auctions are Journal of Mathematical Economics are discussing this, IPL as auction. In India, we heard so many things about this auction thing. Like you heard that spectrum auction, there was illegal thing. Coal mine auction, there was an illegal thing. So suppose you want to do something good for your country. Can you do even with doing quantum mechanics only? The answer is yes. So we wrote papers for quantum sealed bid auction using modified scheme of circular quantum key agreement. I'm not describing this. So I'm just saying that quantum and semi-quantum sealed bid auction. So what is semi-quantum? Here, all the users are not quantum. Quantum resources are costly. So quantum machine can be centrally located and all the contractor who are submitting the quotations may have classical resources or minimal quantum resources. Now, elections are very common in India. So many elections happen. In even veto happens normally, not anonymously, but suppose you need anonymous veto. So these are some of our work. So where we show anonymous veto, experimental realization of anonymous veto, or voting protocol, binary voting. So now, if you can use quantum mechanics to solve auction problem and reduce corruption, and voting can be unrigged or appropriate, absolutely secure voting, then you can strengthen democracy. So by drug designing, you can support optimization, you can support. So there are many ways doing quantum mechanics, you can actually serve the nation. And because of this huge opportunity, which is increasing every day, this is a flourishing field, new field, every day new opportunities is coming. And what else can be done? We don't know. It's what we know, we are just showcasing that this can be done. but there are many other things that can be done using quantum mechanics. And so I was showing that some success stories in 2007 in Geneva, quantum cryptography was used for internet voting for a municipal election, for a small election. We have still miles to go before we can make a big voting using quantum resources. Now, there is something called quantum random number generator. I'll show you that. But before that, you see, a quantum random number generator is a device which uses quantum simple beam splitter, etc., for making a absolute random. Classically, if you toss a coin, if you know how much force you are giving, what is the gravity, etc., you can predict what will be the outcome. You have to solve Newton's law. So classically, there is no ideal random number, but casinos need ideal random number. So here is we show a casino which is using QRNG or quantum random number generator. So when I'm telling, it's just like a storytelling lecture. So when for first time I applied for a funding to establish a lab, and in the lab I want to build quantum random number generator. So I cannot say that I'll sell it to casino, but I had to tell funding agency that who will be my end user. So I told that state lottery board. So state lottery board, DDA, nursery schools, if you have to establish that they are doing an unbiased selection, they have to use a quantum random number generator. Now, UNO can use as privacy, quantum veto, UN can use quantum veto. You can make that our country is corruption free, our election is secure by using, so quantum mechanics can do many things. So normally we divide into 4 vertical. So in our National Quantum Mission also there are 4 vertical. One is quantum computing, one is quantum communication, about which I am talking mostly. One is called quantum sensing. So we can have very high precision measurement using quantum mechanics, and we can beat the classical limits. So we can have, so one product which we expect, which will calculate the value of gravitational acceleration G very accurately. A small change in G will be detected. So what is its use? There can be good magnetometer. So a gravitometer or a gravitational acceleration measures a small change. Suppose you place it in parliament and somebody make a hole, a kind of hole below to come in or something. But then when you remove the mass, there will be change in gravitational acceleration in maybe the 10th digit, and a quantum mechanical system can detect it. A kind of sensor which is, we can have a quantum radar. Already China has claimed that they have built quantum radar, and we can have a handheld NMR. So now you know that NMRs are very big. Sorry, when you use NMR for medical purposes, it's called MRI. So you can have a handheld MRI, something like a metal detector. So computing, our basic thing is to speed up, and we can use all possible realization of qubit. Classically, on communication, you use only photonic qubit because you cannot send other qubit from one place to other place. And then there is quantum materials. The 4th vertical in our national quantum mission is quantum materials. So in quantum materials, what we do, we develop materials with unusual properties or weird quantum properties for use in other technologies. Now, all the discussion today is about quantum information. So I just start some basic ideas. What is information? Anything which you don't know is information. If I tell you now that my name is Professor Anirban Pathak, it's not an information. You already know my name. So you are watching a match, you see that Ronaldo scored a goal. It's an information when you see it for the first time. But then the commentator shouted, "Oh, it's a goal." That's not an information because you already know it's a goal. So what you don't know is information. Next question is information physical? The answer is yes. You see that how information propagates to you. I'm speaking, it's creating a membrane, vibration. That vibration is going through the air. My computer has a catcher, it's catching, it's going through optical fiber, it's reaching you, it's creating again the speaker. If your computer is creating vibration, those are going through air, reaching your ear membrane is vibrating, then there are some neuron. So all involves physical process. So storing information, your hard disk store it like a magnetic dipole. So the dipole is in this side, it is 0. If it is in opposite side, it is 1. In optical fiber, we are sending it in as optics. So every The more you try to dissociate information from physical entities, you will realize that it is impossible and information is physical. If it is physical, laws of physics should be applicable to it. Is there any example? So a simple example is special theory of relativity's postulate is that velocity, so we often say that nothing can move faster than the velocity of light in vacuum. It's not correct. Phase velocity times group velocity is c square. So phase velocity is often faster than c. So it's not true that nothing can move faster than light. What cannot go faster than light? You cannot send the information faster than light. So that means information can propagate faster than light is a law of physics. So laws of physics is applicable to information. Can information be quantified? The answer is yes. We quantify it in terms of beat. It's called Shannon's entropy. So it's a physical quantity. Laws of physics is applicable to it. And best laws of physics known so at the moment is quantum mechanics. So it's the best way to treat information is the quantum information. So keep this in background. Now I quickly, so far I was slow, now I'll be fast. So we use this notion. The whole thing is called bracket. The left hand side I divide, it's called bra, right hand side is called kate. So now you have a vector A1, I hat, J hat, K hat. This I hat, J hat, K hat are your x-axis unit vector, y-axis unit vector, etc. So what you need to describe the vector A? You need this component A1, A2, A3. And one approach may be that I write it like a column matrix A1, A2, A3. So this is what we use in quantum mechanics. And then what is I? I is a vector which is a unit projection along x-axis. So this is 1 and no projection along y and z. So this is 1, 0, 0. So this 1, 0, 0, 0, 1, 0, 0, 0, 1 is my basis in 3 dimension. So if I work in 2 dimension, I don't need the third and I can write this basis as kate 0 and kate 1 and write them as 1, 0 and 0, 1. So that's what we do. So we write my basis as kate 0 is equal to 1, 0, a column matrix. Transpose conjugate of that is called bra 0. Bra 0 is row matrix 1, 0. And then if I take inner product, just like a dot product, you do matrix multiplication, it is 1. And if you take outer product, something else will come. So this is the bracket notation, which we always use. Now, you have an outer product. So simply you write kate A and bra B and check that what is the outer product. So suppose I have kate 0, which is a column matrix 1, 0. You use your copy and do it with me. So bra 0 is row matrix 1, 0. And when I write kate 0, bra 1, so I multiply the column matrix 1, 0 with the bra matrix 0, 1, and we see that I get a 4 cross 4 matrix. So outer product is giving a square matrix, whether inner product is giving me a scalar number. Now we can use this outer product to introduce a gate. So what is a NOT gate? A NOT gate is something which takes 0 to 1 and 1 to 0. So now you see that if I write NOT gate as outer product between 0, 1 and 1, 0. So if it is operate on 0, so inner product between 0 and 0 is 1. So I left with kate 1 and inner product between 1 and 0 is 0. So first term will vanish. While it operate on 1, so the second term will vanish and the first term will remain. So we can write a NOT gate as a matrix. So now we can explicitly write this to adding and then we can see that NOT gate is a matrix. So all these quantum gates are essentially matrix, but we will come back to that. So how visualize it again? So NOT is operating on kate 0. So I write the matrix of the NOT and the matrix of the kate 0 and I get the matrix of kate 1. So operating on 0, it gives 1. Operating on 1, it gives you. Similarly, I have something called Hadamard gate, which is 1 by root 2 plus 1 by root 2 and so on. So this maps 0 as 1 by root 2 0 plus 1 and 1 as 1 by root 2 0 minus 1. So soon you will see that this is just like a 50-50 beam splitter. A 50-50 beam splitter works quite similarly. Now I want to tell you about some different kind of matrix product which you have never come across. I mean, this is not taught in your usual classroom matrix courses. So I have two matrices, AB and CD. So AB and CD can be visualized as AB can be visualized, the column matrix can be visualized as a qubit. It can be viewed like a two-level quantum system. Why? Because you see, your 0 is 1 0 and 1 is 0 1. So what is AB? AB means A times kate 0 plus B times kate 1. So it's a superposition of 0 and 1. And such a state, a two-level system, with position between 0 and 1 is called a qubit. So if you do a measurement, it will collapse to 0 with probability mod A square to 1 with probability mod B square. But anyway, so suppose we have 2 qubit and then you take a tensor product. So how to do the tensor product? A will be multiplied in the left first element of the left side matrix with the entire second matrix. So A times CD, it's AC, AD, BC, PD. So you see, now if you have 2 qubit system, that's a 4 cross 1 matrix. So we are doing something. 0, 1 is 0 tensor 1. So 1, 0 is the 0 matrix for 0 and this is the matrix for 1. But this is a 4 cross 1 matrix. So in the same way, if you increase that, if you have a 3 qubit, triple 1, it's a 8 cross 1 matrix. If you have n such thing, it's a 2 to the power n cross 1 matrix. So it is increasing exponentially. That's not desired. So that's the difficult thing. So if you have a quantum system, an independent particle, the matrices which will work on it is 2n cross 2n matrix. So you see that it works exponential. A classical computer will never be able to simulate. Your laptop can handle something like 2000 cross 2000 matrix. So that is simply 2 to 11 bit. So if you have a 11 qubit system, your matrix computer can simulate to some extent. Not really simulate, but emulate. But if you have 13 qubit, probably your workstation can do it. Or if you have 14 qubit, maybe you have a good workstation which can do it. But what if you have 100 qubit? Though it's matrix multiplication, no classical systems will be able to do it. So Feynman first realized that quantum systems, the Hilbert space increases like tensor product. It grows exponentially fast and classical systems will not be able to simulate it. So then who will simulate it? So one quantum system will simulate another quantum system. So that's the origin of the idea of quantum computer. So now keep this in background and you see that I have a circuit. So you have a Hadamard gate and nothing here. So this means the first qubit is applied Hadamard, second qubit I apply identity, or we apply a combined gate circuit Hadamard tensor product identity on 0 cross 0. So we are just showing this matrix multiplication. So you can do this kind of matrix multiplication easily on your computer, but as the circuit size will increase, your computer will fail to do that. And we often use something called entangled state. So entangled state is very interesting. So what is entangled? So now I'm writing a combined state, 2 qubit state, JIAB, which is 0, 0 plus 1, 1 by root 2. You can see that you cannot distinguish between what is the state of the first qubit and what is the state of the second qubit, which you can do in these cases. If it is 0, 0, you can write it like 0 tensor 0, 1, 0, 1 tensor 0, 0, 1, 0 tensor 1. But so these are separable. Non-separable states are called entangled. In my lab, I produce it by sending a palm beam to a BBO crystal, and that creates two cones. One is horizontally polarized, one is vertically polarized. But when these two cones are superposed, I don't know if this side is horizontal, the other side is vertical. If this side is vertical, the other side is horizontal. So it becomes HB plus VH by root 2 kind of entanglement. This we often produce in our lab. So now, in basic quantum mechanics, we have something called observable. So this observable, physical observable are things which can be measured classically. So you can see me, but I'm not observable. But you can measure my mass, so mass is observable. You can measure my age, so time is observable. You can measure my position, momentum, so position and momentum is observable. So for all such observable, there is an operator, and the operator operates on something called wave function and gives eigenvalue. Or you can see that these are eigenvalue equations. You all expected to know. And those eigenvalues are the values which a real experiment yield, and those eigenvalues are discrete. So for example, for px momentum in the x direction, the operator is minus h bar delta x. So when it will operate on wave function x, it will give me eigenvalue for momentum. So if there are 5 eigenvalues, so only those 5 values can be found in experiment. So if those values are p1, p2, p3, p4, I cannot get p1 plus p2 by 2. So there are some values which are allowed, other values are not allowed. So this discreteness is quantum. Now, Heisenberg uncertainty tells me that if there are observable and two observables don't commute with each other, then I cannot measure them simultaneously with arbitrary accuracy. So now we'll use this for measurement operator for which projects a state A0 plus B1 or alpha 0 plus beta 1 to state 0 is called M0, which is nothing but K0 bra 0. So similarly, I write here Mi. measurement in plus is 1 by superposition state, which Hadamard gate produces 1 by root 2 0 plus 1 by root 2 1. And measurement in plus is this plus gate plus outer product bra plus. So if you don't follow immediately, listen it once again from YouTube. And if you write this explicitly and then try to commute them, you will find that they don't commute. And since they don't commute, I cannot measure them simultaneously with arbitrary accuracy. Now, how to visualize a quantum gate? So we have a time-dependent Schrodinger equation, Hj is equal to H bar del xi del t. If we consider that H is independent of t, and we just do few steps, I see that xi0 evolves to xi2 following this equation. This is just a Schrodinger equation. Now, what is a gate? A gate is something which maps a input state to an output state in unique manner. Every time it will be same. So if you to choose H fix and T fix, every time your input state xi0 will go to same output state xi-t. So every interaction leads to a quantum gate if you can control the interaction time. So this is the visualization of quantum gate. And here we have different quantum gates, which looks like Pauli matrices, and we have different names. And all these gates actually are a small quantum computer. For example, NOT gate does a computation. If you give x, it gives you f of x bar. F of x is computes f of x, which is x bar. So this is how we make circuit. We put Hadamard, input state is 0 0. So after Hadamard, the first qubit becomes 0 plus 1. Second qubit remains 0. So 0 plus 1 by root 2 times 0. So this becomes 0 0 plus 1 0 by root 2. It is separable. And then I'm applying something called C0 gate. So this gate is such that if the first qubit is control qubit, that is 0, nothing happens to the second. If the first qubit is 1, second qubit flips. So it becomes 0 0 plus 1 1, and now it's entangled. So this circuit has a name. It's called EPR circuit. So the idea is that you put many gates and together you make a circuit, and a big circuit is quantum circuit. So what is a qubit? Qubit, as I mentioned, there's a two-level system. So you see, classically, there is a proton and there are electrons. So there is a nucleus and the electron. Electron can be either in the ground state or in the fast state. So this is your bit. If it is in ground state, it is 0. If it is in excited state, it is 1. But quantum mechanically, it is in superposition state. It can be simultaneously in 0 and 1. But when you do a measurement, you find it either in 0 or 1. So with certain probability in 0, certain probability in 1. So this state is written as ket xi is equal to alpha ket 0 plus beta ket 1. And the probability of getting it in 0 is mod alpha square. Probability of getting it in mod beta square in 1. And mod alpha square plus beta square is naturally 1. Now, how to make a qubit? You just think that you have a semi-transparent plate and you are sending a single photon. So it simultaneously gets reflected and transmitted unless you measure it. So when you measure it, what happens? So it collapses to one of the path. So it collapses either to 0 or to 1. Where it will collapse, nobody knows. So even Rajnikant does not know. So that leads to something called quantum random number generator. So I'm sitting with a quantum random number generator. If time permits, last 2 minutes, I'll show you the quantum random number generator. And so it's a very simple thing. You have a single photon source, you have a beam splitter. Post beam splitter, there are two detectors. If this guy clicks, it is 0. If the lower one takes, it is 1. Now, when I was a student, I had to believe my teacher, or I had to believe the textbook, Feynman lectures, etc. But now you can shift the trust. You can believe IBM quantum computer, and from your phone, you can just put a Hadamard gate and put a beam, which is like a beam splitter, and put a measurement gate in IBM quantum computer, and see that if you do one shot, it is 1, sometime 0. If you are doing large number of shots, almost half the times it is 0, half the times it is 1. You can write them and check that they are random or not. Once you see that, create a large random number, you can play with the NIST test and check their randomness. Now, how these things has to do with cryptography? So we have told about quantum superposition. In the right hand side also, you see the technology also. So now a teacher is asking a student, can you give me an example of quantum superposition? Student tell yes, marmaid. So marmaid is half fish, half guard. So teacher told that nobody has seen marmaid. So student told that when you do measure, it collapses either to fish or to a guard. So this is not right. So quantum mechanically, I can make a super state in which the marmaid itself is the basis state. And when we do a measurement in that, then I'll get marmaid only. So now my time is going over, so I will be quick. So there is a beam splitter. This is called Mach-Zehnder interferometer. So now you have a photon. It comes to state 0. After the beam splitter, it become equal superposition in 0 and 1. Now, somebody tell that this is not the case. In the random number generator is working, but if we put, it's like the ball either goes there or there, but the ball is not in superposition. So then if I send 100 ball, 50 will go up, 50 will go down. And then in the next, this is a mirror, it will reflect it. In the next beam splitter, 50 will go up, 50 will go here. So if it is particle-like thing, it's not wave, it's not in both sides, then both the detector would have clicked. But in Mach-Zehnder interferometer, if I send a single photon, I'll see that one detector clicks and the other detector never click. Because one detector, it's coherently interfere constructively, in the other detector, it destructively interfere. And you can mimic these systems by writing 0, 1, the beam splitter as a matrix. So we have written beam splitter matrix and simulate this optics experiment. So these optics are like your quantum gates. So you see the beam splitter matrix is similar to the Hadamard matrix, and you can visualize now a quantum gate. So now how are these useful? So now there is a test called Elitzar-Wedman bomb testing kit. Now you see, this is the Mach-Zehnder interferometer. Ideally, this was supposed to click. And now I put in the picture A, I put a bomb. If I put it in the lower path, if any photon comes and it's an active bomb, it blasts. Now, this bomb is essentially like a detector. So it is detecting which path information, whether the photon is going from this path or that path, just like the detector in random number generator. Now, if it is not in this path, it means this path. So I don't need to put two detectors. Now I send 100 photon. In 50 cases, the photon will be here. But when I know that it is here, provided I put a detector here, and out of those 50, since the wave nature is gone, 25 will click here, 25 will click here. So 25% of the bomb I can detect even without sending a photon. So that's the interesting thing. How that leads to cryptography. Now you see this Mach-Zehnder interferometer. There are two cases. In the left hand side and right hand side, left hand side belongs to Alice, right hand side belongs to Bob. So they are putting randomly two obstacles. So if both of them put obstacles, no photon come, no detector click. If one of them put none of them put obstacles, only D2 clicks. If one of them put obstacles, some cases D1 will click. So whenever D1 will click, that's a success case. Since Alice knows that whether she has put it or not, so if she has not put and D1 has clicked, then it must be Bob. And they decided if it is because of Bob, then it will be 1. If it is because of Alice, it is 0. So soon they will have a big sequence of zeros and ones, which is a key and generated by using quantum resources. And this is called, this is QKD. Now the most popular QKD which we do in my lab is called BB84. So in BB84, we create a random sequence of 0, 1, plus, minus, or 0 is like horizontally polarized, 1 is like vertically polarized, plus, minus are like diagonal and anti-diagonal polarized, and we send it through beam splitter, etc. Mix them. Now, this pink color thing is called polarizing beam splitter. So this polarizing beam splitter allows horizontal photon to pass and vertical photon to deflect. So if this detector on which my mouse is there clicks, then it's definitely horizontal. If this detector clicks, it's vertical. So we say in the protocol, I'm not describing it fully, that we randomly measure it in horizontal vertical polarization or 45 degree, 135 degree. So this beam splitter randomly set in this setup or this setup. And in this setup, you have a circular thing, which is a wave plate, which rotates the polarization by 45 degree. So 45 degree polarized become 0 degree, and 135 degree polarized anti-diagonal minus become 90 degree. And then if the vertical detector clicks, I know that it was 135 degree. If horizontal detector clicks, I know that it was 45 degree. So this is how we do this random measurement. Now, what happens if Eve does a measurement? Since Eve does not know in which basis it is prepared, if Eve choose a wrong basis and measured a plus state in, so plus state is 1 by root 2 0 plus 1 by root 2 1 in 0 1 basis and got 0. So half the time he will choose, because there are two bases only, half the time he will choose incorrect basis and send it to Bob. And Bob measures that again in the right basis, because Alice and Bob keeps only those cases where their basis matches. So in the right basis, and it matches, then they will. So Alice and Bob first compare that in which cases preparation basis and measurement basis are same. They keep only those cases. Suppose 1000 photons are checked, send 500 cases they will match. They keep those 500 cases. Now, if there is a Eve and Eve is randomly trying, so Eve will half of the time Eve will choose wrong basis. So half of those cases will also give correct result, because Just like plus is 1 by root 2 0 plus 1, 0 is also 1 by root 2 plus 1 by root 2 minus. So if a plus state is measured in plus minus basis, ideally it was supposed to get plus, but now 25% of the time it will give minus, and that will detect the presence of if. So this is where quantum cryptography is different from classical. It does not use any computational problem. It is unconditionally secure. It's not conditioned on such problems, and eavesdropping efforts have been detected. Now, many other things, magical things happens in one is quantum teleportation, that a state get destroyed from one position and it's created in the other end, the receiver end. So we are showing a quantum teleportation station here, and you see that this guy goes from quantum teleportation, and after reaching there, his nose and ear has been changed. So that is the problem. That noise is the biggest problem. So we work on quantum teleportation, and sometime we are in the cover of analytic physics also. Now I began with the so I'll almost at the end. So I begin with this idea that satellite-based quantum communication. So how satellite-based quantum communication work? So you already know BB84 that Alice and Bob can create a key. So you see when the satellite is over India, say, so it creates a key. And this is called key 1. And when it is over, say, UK, it creates another key. So that's called key 2. Now satellite makes a XOR of key 1 and key 2 and announce. Station 2, which is located at key, makes XOR with his own key. So key 2 is removed and left with key 1. So now both party has key 1 and they can use key 1 for communication, and satellite is not used here. So you remember the first picture where China and Austria is communicating and the satellite was not there. So many countries are there satellites. They are low Earth orbit satellites, and we are also planning our satellites. So this cartoons explain many things. Here is a quantum girl, and the man is saying that I love quantum girl, but every time I observe you, I found you to be in a new loop. And the girl is answered, that's expected because I'm a quantum girl. Every time you observe, I'll collapse to one of the possibilities. So I'll not elaborate, but there are semi-quantum algorithms. There are computing and communication is connected. There are several computing tasks like auctions, like voting, we need where we need different kind of security measures. So communication and computing goes hands by hand. But unconditional security does not mean unhackable. So still these systems are hackable, but what we use to hack now, we use device imperfection to hack. Here is a very small, nice thing. So there is a circulator. So this is a 3-port device. So if light comes from 1, it goes to 2. And if it comes from 2, it goes to 3. If it comes from 3, it goes to 1. Now you just use Mallows law. So this is Alice's side, this is Eve's side, and Eve sends a strong horizontally polarized, vertically polarized photon. So covering Alice's polarizer, so vertical polarizer 100% will go and change the temperature of L laser diode, and that will change the wavelength. Lambda 1 will become lambda 3, but horizontal polarizer, nothing will pass. So wavelength will not change, it will remain lambda 1 for horizontal. For the other two polarizer, 45-degree relative angle with the vertical is 45 degrees. So by Mallows law, cos square theta, for 50% of the light will go and temperature will change and now wavelength is changed. So though you cannot measure in horizontal, vertical and for 45, 135 basis in simultaneously, but you can measure their wavelength and know which one is what. So this is the attack, but there is a countermeasure. I can put a circulator here and stop light from going inside. So there are other attacks. All the objects which use. I'll stop in 2 minutes.
Pathak, actually, we have a question. One
Okay.
student has asked a question. So can you ask the question?
Yes, please. I cannot see the question. Okay, student can ask the question.
I can recite the question for you. So Mr. Surja Ghosh has asked, can quantum entanglement be used for transportation of information?
Yes, of course. We frequently use it. And there are many protocols which is based on. So even this teleportation thing I was showing, it's actually used teleportation. Actually we use the entanglement between Alice and Bob, and then the information alpha 0 plus beta 1, this is my qubit, which is teleported from this place to this place. So what happens that I already had a qubit. So this qubit in Bob's end got these values of alpha beta, and the alpha beta is lost from the receiver's end. It's not a new qubit, but we often It is a very frequent use. So the message is that unconditional security does not mean unhackable. Every optics we use in the lab is wavelength dependent. Now, so we are more or less at the end. So now there is a Trojan horse attack, a particular kind of attack which can be stopped by circulator. Bob is a boyfriend of Alice and very positive and said that I don't trust you. Alice says why? So because you reflect light. So that's why you can see me, but others can also see you. So to stop others from seeing, you need to give a circulator to stop Trojan horse setup. So here is another cartoon. Alice and Bob is discussing that don't send me messages. My father can see my phone. And Bob is telling that, oh, this is quantum secure. Okay. Now there is another cartoon to show you that what will happen in the quantum world. This will not happen like this dramatic way. So there are two banks. In one bank, everybody is closing the account, but they have 50 years of experience. In another bank which provide quantum security, everybody is opening the account. So this girl is asking this man what happened, and the man is showing that yesterday somebody has discovered a scalable quantum computer and RAC is broken. So that's not going to happen all on a sudden. When quantum computer progress is gradual. And in the abstract, I mentioned that I'll tell you about something about what we do with the undergrads. So here are some adventures in the quantum land with the undergraduate students. So all the names in red are undergraduate students. They were either BSc students or BTech students, and with them. And the most interesting thing is that with Srikara, we designed something called continuous variable quantum secure direct communication protocol, and that was realized experimentally, and that's now called Srikara et al. Protocol. So nobody writes our name. It's known as Srikara et al. Protocol, and Srikara become famous. So the message is that all the undergraduate students or early postgraduate students, that there are problems for everyone, and you can do something, publish it. How the world will change, because I told you that this is a space-time craft. So there are certain things which is now available. Superconducting nanowire single photon detector. This is the best single photon detector. Quantis is my side, means that's a random number generator, APDs, etc. available. So tomorrow certain other things will available, like photon number preserving, polarization preserving, photon number resolving detector, because quantum mechanics allows it, but there is no such things at the moment. But of course, we will not have a cloning machines. So certain things will improve in time, delta, but how much is the delta, I don't know. And for that, we need you. So for the moment, we don't have a good single photon source. So you can develop a good single photon source. We don't have a good single photon detector. So you can develop a good single photon detector for, especially for 1550 nanometer and wavelength independent thing. But we do many things and many aspects. So sometimes we use model environment for satellite assisted communication. Sometimes we do identity authentications. We use game theory for security analysis, because security analysis is always a game. Alice and Bob is trying to hide the information from Eve, and Eve is trying to gain as much as information. So it's a non-cooperative game where Alice and Bob don't cooperate with. So we use the ideas of game theory for security analysis. We use graph theory. So why I am telling this? Because I just want to tell you that whatever be your background, physics has something to offer you. There is always a problem in quantum information. And the last two which we are showing are experimental papers on realization of cow protocol and DPS protocol in our lab. So these are some results in the lab. We will not elaborate, but what I want to tell you that these single photon detectors are not very efficient, and they're very costly. So the detectors shown here, each cost about 26 lakh. Superconducting nanowire detectors are even much more costlier. Our 8-channel detector is about 3 crore. And none of these detectors in built in India. So even if you are not doing something big, make a time tagger for us, make a single photon detector. So we need many companies, many small companies, many startups to build all these things for us. So NQM is there. So the pairs where we have MSc and PhD with this kind of related thing, but that's not the purpose of telling here. But in the right, I'm showing this primarily for faculty and PhD scholar. So CM Chandrasekhar in ISC, popularly we call him Chandru, and me are now editing an issue of Quantum Information Processing Journal called Quantum Information in India, and submission is open till 15th August. And here are some easy reading material. Nielsen Chuang is the best book, but first you read one of the books. For the beginners, I would suggest the read for one of the first 3 books. And now we can show you either I can take questions or show you the a particular quantum product. So just I stop.
Uh, Excuse me, sir. So there are
Uh,
two more questions.
yes, please.
Can I ask them now?
Sure.
Okay, so Mr. Rajratan Meshram is asking if quantum entanglement can transfer information faster than the speed of light through
No,
tunnel and create wormhole.
no. Superluminal communication is not allowed. So the two basic principle is that. So I told you that information is physical and laws of physics are applicable to information. So you can have an apparent feeling. That was the initial of EPR theory, that if there is an entangled state is created, one particle is in here and the other particle is in moon. Say, I do a measurement on the first particle and find that it is a spin up. Then immediately I know that the other particle in moon is a spin down. But somebody in moon does not know. So somebody in moon measures and found it is spin down. So he cannot identify it is because of his measurement it collapsed, or it is because of my measurement. I had already measured it is collapsed. So unless I tell him that I have measured, and that communication cannot be faster than. So even in teleportation, there is a classical communication that this is my outcome, and now you apply this unitary. So that cannot go faster than light. So no way you can do superluminal communication. So signaling is not allowed.
Okay, sir. So there's another question from Mr. Nitesh Sharma. For post-quantum computing, classical cryptography algorithm exists like lattice-based cryptography. For
Yes.
this, can we find, can there be a quantum algorithm found in the future to solve this? And will that be very secure?
Yes, of course, because that's what I told you. I stressed that is post quantum cryptography (PQC). So when I was explaining this P complexity class NP BQP, what I mentioned that these are not proven and it's not provable. So there is no proof that P is equal to NP. P is not equal to NP. So only if it is true that P is a subset of NP, then you can fetch a problem from NP and design this cryptography which will be secure. So now the belief is that quantum computer cannot solve problems other than BQP, but there is no proof. And the belief is that there is a problems outside BQP in NP, and you fetch a problem like lattice and design a cryptographic schemes for post quantum cryptography. But this is a strongly belief conjecture. And we have already seen such kind of example, like Shor's algorithm is an example. So odd biprime factorization was thought to be secure. It is in NP, but in quantum. So the more we will try, the more we will exercise. That's what I was stressing that definitely tomorrow there can be an algorithm. You cannot prove that there will not be any algorithm.
Thank you,
So
sir. As of now, these are the questions.
still the classical cryptography is conditionally secure, and quantum cryptography is better. So PQC is definitely at the moment better paid because PQC does not require. So just like I told you that quantum cloning is not allowed. So in the fiber, I cannot put a repeater. So the problem is that if we cannot put repeater, I cannot make a very long distance communication, and I need dark fiber. So where there is no repeater, there is no joint. So other communication is less. So this is a resource demanding thing. I need single photon detector, but PQC does not require any resource. So even with your laptop, in your mobile phone, you can implement PQC. So at the moment, PQC is expected to give you a better business.
Okay, sir. So there is one more question by Surja Ghosh, who is asking if theoretical physics related research in quantum physics, is that a good scope in terms of future? And this person is curious about that.
So it was always good. Now I borrow something from my PhD supervisor and tell you that it depends on what gives you great comfort. So we often try to solve some integration and we could not do, and then hey, 2 years later or a couple of months later, I realized that a simple substitution could have solved this, and we were idiot for last 4 months. Or so this happens in the research, and that has a comfort that when you rediscover things, eh. So if that gives you a fun, that challenge gives you a fun, then it's theoretical physics your cup of tea. And regarding that, but ultimately you need bread and butter. So theoretical physics at the moment is in such a situation that you will not be in problem with your bread and butter. But if you tomorrow start comparing that one of my friend went to IIM and his salary is X and my salary is eta multiplied by x and eta shorter than 1, then don't come. And physics gives you many things. Means you can travel a lot, you can go to many countries, you can eat different kind of things, yeah, you can see different cultures. So all these are just carried with byproduct of doing theoretical physics or any kind of physics, theoretical or experimental. So as long as you enjoy, it will not frustrate you.
Okay, sir. Thank you for that answer. So there's one more question. Sai Gopal R wants to ask how to join quantum sensor hardware research, and he has a background in electrical engineering.
Oh, okay. So what do you do at the moment? So there are many groups who are doing quantum sensing and quantum sensing hardware. So the hub in National Quantum Mission, we have established a hub, and that is in IIT Bombay. And Kosturi Shaha is the lead. So one thing is the straightforward way. If you have some idea or you want to know the other groups, to drop a message to Kosturi Shaha. You can write. So other people there are many groups who are interested. So Anand Shah and Shaikat in IIT Kanpur, and Kosturi herself is in electrical engineering department. One of my former postdoc, Abhishek Shukla, he works in IMAC in Belgium. So you can find out, or you can ask me for email ID and drop. But if you it will depend on exactly what you want to do. You want to join a PhD program, then there is a formal route. If you want to join as a GRF or something, there are many openings, and just look for National Quantum Mission openings. Uh, and if you want to do some join as an engineer, now that Quantum Sensing Hub also has some opportunities for engineering training or engineering staff, scientist. So it will depend on exactly what you want to do. And if you may send me a precise questions, I can forward you the more precise information and the contacts who can help you better.
Okay, sir. So that would be all from the attendees, I think. So
Yeah,
first of
so-
all, thank you so much.
So just a moment.
Yeah,
So
sure,
I'll
sure.
show you that IBM with this quantities. So this is the packet of the quantities, and yeah.
Sir, if you
And-
can stop your presentation, then the
Oh, okay.
attendees can see you.
Sorry. Yeah. Sorry. Fine. Yeah. Sorry. So you can make my screen bigger just by clicking it. Yeah. And now I show you how it looks. So this is the simplest quantum product. So this has only one beam splitter and two detectors, and it's like laptop charger, and there is a connector. So if we just connect it and connect to your USB port, this will work like a random number generator. But this is different from any classical random number generator. It's a quantum random number generator, but there can be better versions also, which can be a card or things like that. Now, so I'm sharing it once again. So now you can see in your screen that some easy quantum 20.23. So that's the file. And I'm just creating some random number, and you can see this random numbers on your screen. So we have just shown you that quantum mechanically we have created some random number, and you can use it for, say, a bank can use it for sending OTP, etc. So we'll not elaborate on this. Means we can create password, etc. also with this, but just a demo. So I'm finished. Means now if you have any questions, you ask, or we can conclude.
So that's all for the questions, sir. So thank you so much for such a wonderful talk. And this was such a difficult topic as well. I hope all the participants enjoyed the talk. That brings us to the end of the session. Thank you to all of you for joining us. Hope we soon announce the details of the next talk. So please stay tuned to our Instagram page and her Twitter page also. So thank you so much for the attendance.
Thank you all for listening. And if you have any questions, you can drop me mails.
Sir, I think one of the attendees wants to know your email ID. So if you
So
can
that was in
share
the
it.
first slide.
So if you can share it one more time.
It is available on the YouTube channel. So if we check the YouTube channel later, so you will be able to see that.
I'm writing in the chat room also.
Okay.
It's in the first slide. Okay.